So now let's introduce some physics. So the key insight here is that c, the speed of light, is the same let's say for all values of v. So you can move with some speed v. That v can be anything. It can be 0 up to some large value, let's say. And in your moving spaceship, if you will, it'll turn out that you'll always get this same value if you measure the speed of light. So in other words, in some sense, you can't catch up to light. Light is moving with respect to you at the speed c, at the same speed, regardless of how fast you're moving. That's an amazing fact, and everything that we're going to look at follows from that fact. So we're going to try to find a way of describing on a space-time diagram this idea that we can imagine comes from experiments. So x and t, and we have, if we launch a particle of light to the right on the space-time diagram, it's going to be 45 degrees. That's c. And I want to now find a way of describing what happens given this idea, which we imagined is coming to us from experiments. So if there are two experimenters or two observers that are moving with respect to each other at some speed v, so you could think of yourself being at rest and the other experimenter or observer moving with respect to you at speed v, both of us need to measure the same speed of light c. That's an amazing fact. So we're going to try to figure out how to incorporate that on the space-time diagram. And so what we're going to find out is that what we need to do is to change space and time in a way that depends on how you're moving. So if we consider ourselves at rest, then space and time can be described this way, and the speed of light to the right involves diagonal lines, 45-degree diagonal lines. Now let's try to figure out what that looks like for an observer moving with respect to us at speed v. Now, of course, according to that observer, we are the ones that are moving at speed v in the opposite direction. So let's consider ourselves at rest and imagine our motion through space-time, our motion on the space-time diagram, if we're just sitting there and not moving. So our value of v is 0. Of course, those are just vertical lines, right? If we're not moving through space-time, our lines, our paths on the space-time diagram are vertical lines. And that's just the time axis. So the way we're moving on the space-time diagram is our time axis. Okay? So that's key. So now let's consider, so first let's write this down. So consider ourselves at rest. So in other words, with v equals 0, this is vertical motion on the space-time diagram, space comma t diagram. Okay, so our motion is all in time, and we move along the time axis. So we can identify the time axis for moving observers by the same idea. So a moving experimenter or observer moving at speed v, which of course has to be, well, actually that comes from the theory, but let's say that the observer is moving at some speed which is less than the speed of light. what does that look like on the space-time diagram? So if this is the way we measure time and the way we measure space, and this is the speed of light, then if we're both we both start at this, we both meet up at some moment in space and at some moment in time, some location in space at some moment in time, here t equals 0, x equals 0, then this observer's motion is going to be a line that's tilted more toward the vertical, more toward the time, than toward the x-axis because of this condition. So this would be something like that. Okay, so given that either of us can be considered at rest, right? So the results of experiments are all the same. You'll find the same results of experiments in one laboratory or the other. There's nothing special there's no absolute notion of v. Okay, so that observer is moving with respect to us at speed v. We are moving with respect to that observer at speed v. We're all the same. So this can be considered, from our perspective, the time axis of the moving observer. Okay, so we've gotten that. And so what about the spatial axis? Well, a simple way of thinking about this is that there's some angle here, say theta, given by how fast this observer is moving. So in fact, the tangent of this angle is the speed of this observer, because it's just the opposite over the adjacent, and that's just the distance traveled horizontally over the time that passes vertically there. And we could argue that the spatial axis has to be such that as v goes to 0, so that the speed of that observer goes to 0, they're going to have the same time axis as we are. And so the spatial axis has to reduce to our spatial axis. And so that would suggest simply that x and t, from our perspective, speed of light, t bar, let's say, with some angle theta, and x bar at some angle theta. Right, so the speed of light is always the same, so it doesn't change on the space-time diagram, but space and time change. They have to tilt upwards by the same amount, such that the speed of light is always the same. Another way of thinking about this is that if we want to get the spatial axis, right, we know that x is horizontal, t is vertical from our perspective, but if at this moment in time we send a particle of light outwards to the right, and it's located, say, at this location here, x, then light travels at 45 degrees on the space-time diagram. So it's going to hit and get reflected from, say, a mirror and come back to us at 45 degrees. And so we know that this is the halfway time, right? This is halfway in between in terms of times. And when we connect this point to where the mirror is there, that gives us the spatial axis. And of course, it's perpendicular to the time direction because of these two times being the same. But if we think about this from the, say, perspective of the moving observer, then here's t and x, and we argue that this is t bar for the moving observer. If I take that axis and move that down there, then here is an earlier moment in time compared to t bar equals 0, where we launch a particle of light, and this particle of light travels at 45 degrees, hits a mirror here, and then travels back 45 degrees along here. Not the best drawing, but what we get is that time in between these two is below here, because this is tilted this way, so it's really somewhere down in here. My drawing wasn't very good, but then this makes, and that's even worse. Do this again, but that makes the x bar axis go like that. Let's draw this again. So t x, let's simply start at 0. So this is speed of light, and this is the t bar, time axis for the moving observer, and this is where the mirror is. So it's right here, and then it hits the mirror and gets reflected backward, another 45-degree line for light moving to the left. And so now we can see that this time and t bar equals 0, we have to divide that by 2. We get something in here, and then we connect that to that point there, and that must be the x bar axis. And so the key is that the speed of light is always in between the space and the time, and essentially the spatial axes and the time axes close up toward the speed of light on the space-time diagram. That's how we ensure that light is always the same regardless of motion.